I'm Anil Kumar. Welcome to my series on probability. Here is an assignment shared by a student which I am going to discuss in this particular video. In case you want to learn from me, you can always send me an email on the address given here. We'll discuss 7 questions. I hope these questions and their solutions will help you prepare for your examination. So the questions here are: question number 1. During a flu epidemic, 35% of a school students have the flu. Of these with flu, 90% have high temperatures. However, a high temperature is also possible for people without flu. In fact, the school's nurse estimates that 12% of those without flu have high temperature. Draw a tree diagram about what percent of students have high temperature. If a student has high temperature, what is the probability that the student has the flu? Question number 2. Two fair dice are rolled. What is the probability that one die lands on 6 given that the dice land on different numbers? Question number 3. A reduced deck of 4 jacks and 4 queens is shuffled. If two cards are picked at random, what is the probability that both are jacks? The second is queen, given that the first is jack. One is a queen, given that at least one is a jack. So these are the 3 parts which you need to answer, correct? Now let's look into question number 4. I'd like you to actually pause the video, copy these questions and answer them. Question number 4 here is: a customer visiting suit department of a certain store will purchase, these are different conditions given to us, a suit with probability 0.22, a shirt with probability 0.30, a tie with probability 0.28, a suit and a shirt with probability of 0.11, a suit and a tie with probability of 0.14, a shirt and a tie with probability of 0.10, all 3 items with probability of 0.06. And what you need to find is, first you need to draw the Venn diagram, and then what is the probability that a customer purchases one of these items. Now here are question number 5, 6 and 7. In question number 5, we are given probability of event A, which is 0.43, probability of event B is given to us as 0.31, and the probability of A union B is given as 0.61. You need to find the probability of A intersection B, probability of complement of A union B, probability of A complement intersection B, and the probability of A union B complement. Question number 6. Vase A contains a red flower and 2 white flowers. Vase B contains 2 red flowers and 2 white flowers. Vase C contains 3 red flowers and 1 white flower. A die is rolled. If an even number comes up, then a random flower is picked from the vase A. If a 1 or 3 comes up, the random flower is picked from the vase B. If any other number comes up, a flower is picked from vase C. What is the probability of picking a red flower? B is, if a red flower is picked, what is the probability that it comes from vase C? Now here is the last question which we are going to discuss, which is, a study shows that in 1991, 31.6% of men and 35% of women were obese. In 1991, 48.7% of Americans were men and 51.3% were women. What is the probability that a randomly selected American is an obese male? B. What is the probability that a randomly selected American is obese? C. Are the events is obese and is male independent? How do you know? So these are the 7 questions. You can pause and answer and then look into my solutions. Let us begin with the formula sheet to understand and review the concepts learned. So we learned that the probability of an event is the ratio of favorable to the total number of outcomes in the sample space. We also know that the sum of the probability of the event and its complement is always 1. Now, probability of A union B is probability of A plus probability of B. Take away the probability of A intersection B, right? Well, in case we have a mutually exclusive event, in that case, the intersection of the two events will be a null set, and therefore the probability will be sum of their probabilities. In case of independent events, the probability of A intersection B is the product of the probabilities of A and B. Perfect. Now let's look into our learnings on conditional probability. If B, we want to find probability of B if A has occurred. In that case, it is intersection of A and B divided by the probability of A, as shown here. Now, in case of, you can actually cross multiply and rearrange the formula to write it in the product form, which is probability of A intersection B is probability of A times probability of B when A has occurred. So you can always say that this is your general equation and is known as the product formula. In independent events, as you know, the probability of B when A has occurred will be probability of B since it is an independent event. So for independent events, probability of B will be equal to probability of B when A has occurred. But for dependent events, it will not be the same, right? So that's kind of important to understand that for dependent events, probability of B when A has occurred is not equal to probability of B. Now, these are few formulas which you might use. We will not be using them in this set, where the permutation formula, the combination formula, and the factorial formula given for reference. Now, let us see how to answer these questions one by one. Question number 1. During a flu epidemic, 35% of school students have flu. Of those with flu, 90% have high temperature. However, a high temperature is also possible for people without flu. In fact, the school nurse estimates that 12% of those without flu have high temperature. So first thing is we need to draw tree diagram. So two critical parameters to consider. One is flu and the other one is high temperature, right? So these are the two things. Now from here clearly we are given that 35% students have flu. So that means that is 35% students having flu. So if that happens, in that case, 65% will not be having flu, correct? Now out of these, we are also given that 90% have high temperatures. So the 90% have high temperature. So when you multiply them, we get the probability or the number of percent affected by flu which have high temperature, correct? However, the high temperature is also possible without flu, and it has been estimated that 12% of those without flu will also have high temperature. So the high temperature also exists for 12% of those who do not have flu, right? So that is the other arm of our interest. So we have a tree diagram right there. So all these values are calculated as written. So you can do that. Now let's answer part B, which is what percent of students have high temperature? So when we say high temperature, so we have to look into these two groups. So those with flu and those without flu. So basically we can just add them up and then we get a value which is 0.393, approximately 40% have high temperature. Now the next question here is If a student has high temperature, what is the probability that the student has flu, right? So now we have high temperature because of two reasons, right? So which ones come from the high temperature and flu combination, right? So that is a conditional probability. So we need to find that given that the temperature is high, out of that, how many have flu, right? So it is probability of flu intersection high temperature divided by probability of high temperature. So we know by adding up, as we did in the first case, 0.393 are total number of people affected which have high flu, but only with which have high temperature, right? So this is total with high temperature. And amongst these, those with high temperature and flu are given to us as 0.315. So put that in the numerator, divide and get your answer. It comes to 80% of those with high temperature also have flu. Okay, so I hope that helps. Now let's take up question number 2. Two fair dice are rolled. What is the probability that only one dice lands on 6 given that the dice lands on different numbers, right? So when you roll a die, we're looking into the condition when both are landing on different numbers, right? And we are also looking for condition that one die lands on 6, right? So we are looking for a conditional probability, one die on 6 and different numbers. So in this case, as you can see, it's a conditional probability case. We can restrict our sample space to the outcomes which do not include same numbers, right? So the complement of that. So in our case, the sample space will be 36 minus 6, where the 6 which are excluded are shaded here, right? So they have the same numbers. So they have been excluded. So once you exclude that, you are left with 30 options. From the matrix which you have shown here, so what we've done here, we have shown die 1 here in one direction, and the other direction shows the second die, right? So one die and the second dies. So when you have these two dies, the numbers are recorded. So we have 30 different numbers, out of which those which have 6 are highlighted here in circles, right? So you can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is 10 out of 30 which gives us the right answer. Is that clear to you? So, so this method really helps. So 10 out of 30 are showing us 6 when both the dice have different numbers. Example 3. A reduced deck of 4 jacks and 4 queens is shuffled. If two cards are picked at random, what is the probability that both are jacks? Now, let's look into this case. We only have 4 queens in the deck now and 4 jacks to work with, right? That is what it is. So that is the reduced pack of cards which we are working with. So now picking up a jack or a queen is 50-50, right? So that is a 50% probability. Now it says, and if the two cards are picked at random, what is the probability that both are jacks? So if you want both as jacks, that means probability of picking up a jack is half. Once one jack has been picked, then one less has remained, right? So instead of 4, we are remaining with 3 jacks, and total number of cards also reduced from 8 to 7, and therefore their probability will be product of half and 3 over 7 as shown here, which comes out to be 3 over 14, correct? So that becomes our answer for the first case. Now in the second case, the second is a queen given that the first is a jack. So we are given that the first one is a jack and the second one is a queen. So that means first one jack and second one queen, and that is what we are looking into. And so we get our answer. Now in this particular case, what we are looking into is first it says the second is queen given that the first is jack. So probability of first being jack is half, right? That is the probability of first being Jack, and that is half. And now we see second being Queen will be half into 4.4 over 7. So we get our answer as 4 over 7 as shown here. Correct? Part C. 1 is Queen given that at least 1 is Jack. Now that is kind of very important to understand. At least 1 is Jack. That means what? That really means that we have to take away both queens portion, right? So it's a complement of both queens, correct? So it is kind of complement of both queens. So what we do is 1 minus the probability of getting both queens, correct? Which is 1 over 2 times 3 over 7, correct? So that comes in the denominator as the probability of getting Jack, 1 Jack, correct? That means not a queen. So that goes into the denominator of conditional probability, and we are looking for 1 queen, and 1 queen definitely is the case when we are having this particular case as in the previous one, right? Jack and a queen. So that gives you only 1 queen, and so their ratio gives us the probability as shown here, 4 over 11 being the answer. So I hope the concept is clear. Look at it carefully to understand these conditional probability questions. Example 4. A customer visiting a suit department of a certain store will purchase. So we are given different conditions here of purchasing different types of items, correct? Now, we have to draw a Venn diagram. That is the first thing, to draw a Venn diagram. And then we have to answer a question. Well, remember one thing, that you could answer the question, let's say part A and B. So let me say this is part B, and here's the Venn diagram. You could answer the question even without drawing the Venn diagram. Is that clear to you? Right. So I've given you a solution here, which is directly without even drawing the Venn diagram. Sometimes, it is good to check your solution also, right? You get an idea. So note, can provide solution of part B even without the Venn diagram. Is that clear to you? At least it helps to check solution, right? So that is kind of very important. And the idea here is what you do is you just add the probability of all individuals, taking away the probability of intersection of two of them, right? And then adding the probability of all three of them. And that is how you get your answer, which in this case is 0.51. Clear? So that is straight away doing this. Now let us see the strategy to make a Venn diagram, right? So let's study the strategy. So to begin with, it is important to begin with the intersection of all three. So that is the strategy. So strategy is begin with intersection of all the conditions. Okay, so in this particular case, we know that all three items with probability of 0.06, so that is the cell which you have to fill in first. You get the idea. And then you move from there, right? So then outwards. So you have a base here, right? So now when you do that, the shirt and a tie with probability of 0.10. So shirt and a tie. So three circles representing suit, shirt, and the tie. And this is the intersection of shirt and the tie. So which is 0.10. Take away what is common to all, right? 0.06. And when you do that, you get 0.04 as your answer. So that is how you have to do it, correct? So the next one will be suit and a tie. So when it comes to suit and a tie, so we're looking into this portion, right? So definitely, again, what will you do? You will take away from 0.14 the intersection of all three, which is 0.06, to get the value of 0.08. Does make sense to you? So that is how you have to go outwards from inside. So once you do that, you have your solution right there as shown here. Perfect. So that is how you're going to sketch the Venn diagram. I hope the concept is absolutely clear, right? Now let's move on and check the solution for example 5. Now in example 5, we are given probability of A, probability of B, and probability of A union B, correct? So we have to now find probability of A intersection B. How will you find this? Well, probability of A union B is probability of A plus B, taking away probability of A intersection B, correct? So basically, you need to rearrange the formula, right? To find the intersection. Is that clear to you? So that is how you're going to do it, and that is how we get our solution. So you can take probability of A intersection B on the left side, union on the right side, substituting the values, we get our solution. The part B is A union B and complement the simple 1 minus, right? So this is just a complement. So we get this as a complement. Correct. And part C is, now we need to consider the probability of complement of A intersection B. Now what does that mean? Let's try to understand this part and then we'll look into the solution. So it is intersection of not A. So not A means what? Not A means this, correct? So this is not A. Is that clear to you? Everything outside A is not A. Now, but intersection of B. So out of this, what really intersects with B is what you're looking into. So not A, but intersection of B is this is the portion which you're looking into. Is that clear to you? So that means it is B without the intersection of A and B. Is that clear to you? So that is what we did. So now we have our formula for A union B. Sorry, part C, right? So let me highlight with lighter ring. So not A intersection of B as shown here clearly is probability of B, and from that we take away the intersection part, right? We already found the intersection part A, substituting that value, we get our answer. So I hope that is absolutely clear. Now, the next portion is probability of A union not B, right? So now let's look into this part. Probability of A union and not B. So let me erase this and then fill this out. So this case, we are saying probability of A union not B. So when I say not B, I mean this portion, correct? Not B. So that is not B for us. Correct. Union with A. So we have to add to this whatever is A for us. So in not B, we added the intersection. You see that? So we have not B, and then to this, we added the intersection to get our result. Perfect. So that is how we are going to answer this particular question. So really speaking, Venn diagram helps. So clearly, you can draw a separate Venn diagram for each one of them and then do such questions. Clear? Now let's take the next example, which is example 6. Vase A contains one red flower, two white flowers. Vase B contains two red flowers and two white flowers. C contains three red flowers and one white flower. A die is rolled. If an even number comes, which is 2, 4, and 6, right, then a random flower is picked from A. If 1 or 3 comes, Then a random flower is picked from B. If any other number comes, random flower is picked from C. Find the probability of picking a red flower. So, okay, so let's draw in different ways you could do it. You could either draw a tree diagram to help. In this particular case, I actually have drawn the table. So these are the ways A, B, and C. As you can see, A has 1 red, 2 white, B has 2 red, 2 white, and C has 3 red, 1 white. Now when we have even numbers which are 2, 4, and 6, a flower is picked randomly from vase A. For the numbers 1 and 3, flower is randomly picked from vase B. For any other number, which in this case is 5, flower will be picked from C. Correct? Let us see how to solve this particular question. We'll find the probability of picking a red flower. So red flower will be picked based on what is the number on the dice. Correct? So if the number is 2, 4, or 6, so what is the probability of this? 3 numbers out of 6, right? Um, Now, in that case, you pick a flower from vase A. And in vase A, there's only one red out of total 3 flowers, right? 1 plus 2. So therefore, we get probability of getting the number is 3 out of 6 times of getting the red flower is 1 out of 3. Perfect. Now, for picking up the second flower red from the second vase, which is B, the numbers could be 1 or 3, which is 2 out of 6. And the probability of picking a flower in this particular case is 2 out of 4, right? So there is a error here. So there are two numbers and 2 out of 4, which is half, right? So let me write 2 out of 4. Okay, so we'll do some recalculation here. Now, the number 5 is the only number which will help you pick from vase C, which is 1 over 6, right? And here we have 3 red out of 4, so that is 3 out of 4. Let's recalculate the answer and see what do we get, right? So in this case, we get 3 and 3 cancel, so we get 1 over 6 plus, here we get 4 cancels, again 1 over 6 plus, we get 6 goes 2 times 1 over 8, right? So that gives us 24 is the common denominator, and that gives you 6 times 4 is 24 plus 3. Correct? So 8 and 3, 11. So 11 over 24 is correct. So this calculation is correct. Okay. So we have 11 over 24 as the probability of picking up a red flower. Now, part B here is, if a red flower is picked, what is the probability that it comes from vase C, right? So this is what we have to now look into, that it comes from vase C, right? Let's look into this portion now. So that means a conditional probability. So what is the probability of picking up a red flower in all? We already calculated first, we calculated the probability of red flower, which is 11 over 24. So that goes into the denominator, and in the numerator, the probability of picking up the flower, red flower from vase C. It will be picked only if 1 out of 6 is the probability for picking up the vase, and then 3 out of 4 is of the red flower. And that simplifies to 3 over 11, and that becomes our answer. So I hope that is absolutely clear. Now let's look into the last question, which is, a study shows that in 1991, 31.6% of men and 35% of women were obese. In 1991, 48.7% of Americans were men and 51.3% were women. What is the probability that a randomly selected American is an obese male? What is the probability that the randomly selected American is obese? Are the events is obese and is male independent? How do you know? So a tree diagram can really help us answer these questions, correct? So let's begin by sketching the tree diagram. We are given that 31.6% of men and 35% of women are obese. Now, in 1991, 48.7% 48.7% of Americans were men and 51.3% were women. So let's begin with men and women probabilities. So men were given 48.7%. We are given that 31.6% of men. So from here, 31.6% are men, which are obese, right? So we get that data. And so remaining are not obese. So 1 minus that will give us not obese. Similarly, we can now do the other branch, which is about the women, which is 51.3%. And in the women, we are given that 35% are obese. So that fills up the other part also, not obese, by doing 1 minus that. Now let us see how to answer these questions. So, part A, what is the probability that a randomly selected American is an obese male? So, when you're looking into obese male, we know this is male and that is obese, right? So, we can multiply that first arm right away to get our solution, right? So, that gives you the answer. Part B is, what is the probability that a randomly selected American is obese, right? So that means we are now looking into it could be a man or a woman. So both could give us, and therefore we combine the two arms and get our answer for part B. Part C here is, are the events is obese and is male independent? How do you know? So we learn that for independent and dependent, we could find the product of probability of A and B. If that is same as probability of A and B, in that case they are independent. Otherwise, they are dependent. So let's just multiply the probability of being obese and probability of being a male. And that gives you the value as 0.105. And this value, as you can see, does not match with the value which we calculated in part A. Since they are different values, we can say that these two are not independent events, they are dependent events. Is that clear to you? So with that, we come to an end of our solution to the assignment, and I hope this really helps you to understand how to solve probability related questions uh, as we've done here in this particular video. Feel free to write your comment, share your views, keep sharing your questions and assignments so that we have good variety of questions to discuss with our students. So thank you once again for sharing and uh, learning. Thank you and all the best.